Hello and welcome to the BS Academy. We hope that your preparation is going well. So let's start the next video.
Now the second chart of fluid mechanics includes there are 4 chapters. First one is the fluid dynamics, then after the laminar flow, then after the turbulent flow, and the last one is the flow through pipes. Let's begin with the first one, which is fluid dynamics.
Before that, if you are new to your academy, then please subscribe for the upcoming videos and the links for the short notes which are in description box.
So here in the fluid dynamics, first one is the definition of the fluid dynamics. It is the study of motion of fluid under the influence of various forces is called the fluid dynamics. And there are two forces are there. First one is the surface force, which acts on the surface, and the example is shear force and the pressure force. The second one is the body force, which acts on the body at the centroid of the fluid element, and the examples are like self-weight and the centrifugal force, and the last one is the inertia force. Then after there is the Euler's equation of motion is there. Equation for that, sigma F is equal to ma and Fp plus Fb is equal to ma. Then after Navier-Stokes equations are there. Fp plus Fb plus Fp plus Fi is equal to 0. For Navier-Stokes equation, you have to remember these three equations in the form of x, y and z. These are very simple, like for x direction, mu into del square u minus del p by del x plus rho into gx, which is equal to rho into du by dt. Now for y direction, it is very easy to remember that you have to replace the u by v and x by y. Similarly, for the z direction, you have to replace the w in the place of u and z in the place of x. Then after Bernoulli's equation is there, p by rho g plus v square by 2g plus z equal to constant, and the other is p1 by rho 1g plus v1 square by 2g plus z1 is equal to v2 by rho 2g plus v2 square by 2g plus z2 plus hf. Here hf is equal to head losses, and there are some assumptions which are taken in the Bernoulli's equation. First one is the flow should be incompressible, then sturdy flow is there, then ideal fluid, then after applicable only along the streamline, and no heat or external work interaction in the flow. Then there is bit of 2 equation is there. P stag is equal to P state plus rho square by 2, and H is equal to P stag minus P state upon rho g. Here P state is equal to static and stag for stagnation point. Then after Torricelli's equations for velocity, v is equal to under root 2gh, then bit of tube or Prandtl tube for static, v is equal to root 2gh, and h is equal to x into rho m by rho minus 1, which is equal to p stag minus p state by rho g. Here p stag minus p state is equal to manometric height. Then after Venturimeter, it works on the Bernoulli's principle, and in the converging portion v will increase, p will decrease. Then for the diverging portion, v will decrease and p will increase. Then the equation of v2 square minus v1 square by 2g is equal to h1 minus hf, and q is equal to cd into a1 a2 upon under root a1 square minus a2 square into root 2gh. Then after orifice meter and nozzle meter, q is equal to cd into a1 a2 upon under root a1 square minus a2 square into root 2gh. Then momentum equation is there. Sigma f is equal to m dot into v out minus m dot into v in plus L by del T into m dot into v bar at control volume. Then this table you have to remember. For Venturimeter, the losses are low, then CD is equal to 0.95 to 99. Then cost is higher and accuracy is also higher. Similarly, for the nozzle meter, losses are medium, then CD is also 0.7 to 0.8 and cost is medium, then accuracy is medium. And for orifice meter, losses are higher, CD is lower, 0.55 to 0.7, cost is low for the orifice meter and accuracy will be lower. The impact of jet, for that there are two types. First one is for free plate and second one is for curved plate. The equation for the free plate are, first one is F is equal to rho a v square for normal impact on fixed plate. Then after F is equal to rho a into v minus u square, which is for plate moving in the direction of jet. Then the third one is for moving inclined plane. Fn is equal to rho a into v minus u square into sin theta, and for fixed inclined plane Fn is equal to rho a v square into sin theta. Then similarly for the curved plate, F is equal to rho a v square into 1 plus cos theta, F is equal to rho a into v minus u square into 1 plus cos theta. Then after moving inclined plate, Q1 is equal to Q by 2 into 1 plus cos theta and Q2 is equal to Q by 2 into 1 minus cos theta. Here jet strikes on the inclined plate, the oblique impact on the fixed flat plate. So you have to use Q is equal to Q1 plus Q2 and theta is equal to 90. So Q1 is equal to Q2 is equal to Q by 2 for theta is equal to 90. Then after for plate mounted on the periphery of wheel, then Fn is equal to rho a v into v minus u and omega n is equal to Fn minus u. Then force exerted by a jet on a hinge plate, then Fn is equal to rho a v square into sin 90 minus theta, and for equilibrium sin theta is equal to rho a v square by w, where w is equal to mg. So this is all about the fluid dynamics. Now the second chapter is laminar flow. For laminar flow, Re should less than 2000. Then for translation flow, Re should be between 2000 to 4000, and for turbulent flow, Re should be greater than 4000. Here Re is Reynolds number. Then for hydrodynamic entrance length, Le by D ratio is equal to 0.05 into Re for laminar flow, and Le by D ratio is 4.4 into Re is to 1.6 for turbulent flow. Then there are three examples are there. First one is for finding the value of omega. Then after the second example, you have to find the R and Y, and the third one is for finding the value of tau. And the third concept is for laminar flow through circular pipe. Here shear stress tau is equal to minus dp by dx into r by 2, which is equal to minus mu into du by dr, which is equal to mu into u by h. The last two equations for laminar flow. Then u is equal to u max into 1 minus r square by r square, and here small r is equal to r by root 2. Then v average is equal to u max by 2, and del p is equal to 32 into mu v average into L upon d square. Here t omega is equal to del p by L into d by 4, and tau is equal to 2 into mu into u max into r upon r square. Then hf is equal to del p by rho g, and t omega is equal to 2 into mu into u max upon r. Then fourth one is Cote flow. For this flow, one plate is fixed and the other plate is parallel to the first one, and which is moving with the velocity of u. These questions were asked in the GATE examination. Then after, if p1 is equal to p2, then dp by dx is equal to 0, and if p1 greater than p2, then dp by dx less than 0, and if p2 greater than p1, then dp by dx greater than 0. Then for laminar flow between two large fixed parallel plates, you have to remember these equations of tau, u, then v average and del p, as well as the tau max at y is equal to 0 and v max at y is equal to h by 2 for the laminar flow between two large fixed parallel plates. Then there is the topic of pipe networks, and there two types are there. First one is pipe in series and the second one is pipes in parallel. For pipes in series, Q1 is equal to Q2 is equal to Q3 is equal to Q, and del P is equal to del P1 plus del P2. Then HF is equal to HF1 plus HF2, and FL by D raised to 5 is equal to F1 L1 by D1 raised to 5. Then for the pipes in parallel, then for the pipes in parallel connections, Q1 plus Q2 is equal to Q, and del P is equal to del P1 plus del P2, then HF is equal to HF1 is equal to HF2, and under root D raised to 5 upon F into L, which is equal to under root D1 raised to 5 upon F1 into L1. So from these last two equations, for the series and parallel connections, the questions were so many times asked in the examination. So just remember the fourth equations of both the types. Then fifth one is the kinematic connection. Then fifth one is kinematic correction factor alpha is equal to 1 upon AV cube into integration U cube into dA. Then alpha is equal to 2 for laminar flow, and alpha is equal to 1.05 to 1.7 for turbulent flow. Then after momentum correction factor, beta is equal to 1 upon A into V square into U square dA. Here V is equal to average velocity, U is equal to local velocity at distance r, and beta is equal to 4 by 3 for laminar flow, and beta is equal to 1.01 to 1.03 for turbulent flow. Then laminar flow through inclined planes, the equations are there. T is equal to minus dp star by dx into r by 2, where p star is equal to p plus rho gz. Then the equations of u max delta p stars, and u is also there. Here the equation of u is very important. U is equal to minus h square upon 2 mu into dp by dx, and y by h minus y square by h square. Then u max is equal to 1 minus r square by r square, and del p star is equal to 32 mu v average L upon d square. From these four equations, there are so many times questions were asked. Then there is one other diagram is there for the TEL, where TEL is equal to total energy line, and HGL is equal to TEL minus KE, where HGL is equal to hydraulic grade line and K is equal to kinetic energy line. And HGL may be fall or rise, this you have to remember. Next chapter is the turbulent flow. For this chapter, there are some equations are important, and some concepts are for your knowledge, because sometimes the questions will ask from these concepts also. First one is the Reynolds experiment. For that, three diagrams are there. Then after, the time average velocity is there. For that, u bar is equal to 1 upon t into integration of 0 to t into u dt, and for v bar and omega bar, the equations are similar. Then time average of the fluctuating velocity, u bar is equal to 0, and for 1D turbulent flow over the flat plate, the equations of viscous stress, Tv is equal to mu into du bar upon dy, and Tr is equal to minus rho into u dash into v dash bar. Then Tr is equal to minus rho into L square into du bar upon dy bar. Here it is near to surface the value of stress. Then there is a note there which is most important. At higher Reynolds number, there is different value of k by d, and surface reference will be higher, it will be increased, and F is equal to phi of Re and k by d. Then after turbulent flow through circular pipe, for this type of flow, rho is equal to 11.6 into mu upon mu star. Then tau is equal to minus dp by dx into r, and u is equal to u bar max into 1 minus r by r raised to 1 by 7. And hydrodynamically smooth surface, for that k is less than 0.25 into dv. Here k by del v is less than 0.25 for the hydrodynamic smooth surface. 5 equations. First one is u bar by v star, then second one is for u max by v star, third one is the u max bar minus u r bar upon v star is equal to 5.75 log r upon r minus r, Then the fourth one is mu by mu star is equal to 5.75 log 10 into r v star by v plus 1.75. Here r is equal to 0. Then fifth one is u max by v is equal to 1 plus 1.33 root 5. So these are the equations. You can take a screenshot and note down in the book, because in the short notes we have covered only the equations which are important. So you just need to take a screenshot and write down at your own. Then there are two notes are there. You can take a screenshot if you want. First one is for f is equal to 4 into f dash, and for 3D turbulent flow there are 9 components of Reynolds stress are present. The next chapter is flow through pipes. Here two types of losses are there. First one is for the major loss and the second one is for the minor loss. For the major loss, delta P is equal to 32 mu L upon d square and HF is equal to FL V square by 2GD. These two equations are very most important for the examination. The first equation is known as the Hagen-Poisson equation. The second equation, HF is equal to FL V square by 2GD, is known as the Darcy-Weisbach equation. Here remember that F is equal to 4 into F dash, where F is equal to fanning friction factor and F dash is equal to friction coefficient. Then HF is equal to 32 mu L by rho GD, which is for laminar flow. From these three equations, questions were so many times asked in the examination for finding the ratios of F by D or L by G or any other ratios. So you have to remember these equations. Then the head loss due to the friction is given by the Darcy-Weisbach equations. Here as you can see that HF is equal to FL V square by 2GD, then HF is equal to FL Q square upon 12.1 into d raised to 5. This is also important in the examination. You can use, as you can see that HF is proportional to L by d raised to 5 and HF is proportional to delta P by rho G. Then F is equal to 0.3164 upon RE raised to 0.25, which is Blasius equation. Then after for turbulent flow, rough surface 1 upon root 5 is equal to minus 2 into log 10 into R by K plus 1.74. Then in the laminar flow, F only depend on the RE and independent from the K by D. Then for non-laminar flow, 1 by root F is equal to minus 2 into log 10 into K by D upon 3.7 plus 2.51 upon RE into root F, which is known as the Colebrook equation. Then there is one example for Q proportional to d raised to 4 and delta P proportional to V raised to 1.8. Then Moody's curve is there. The graphical representation of the Moody's curve you can see there. Then equation based on which this curve is made, the equation is of Colebrook equation. Then after for minor losses, first one is for loss due to the sudden contraction. The equation is HL contraction is equal to VL square by 2G into 1 by CC minus 1 square, where CC is equal to SC upon AL coefficient of vena contracta. Then after second one is loss due to the sudden expansion. HL expansion is equal to V1 square minus 2 into V1 V2 plus V2 square by 2G. Then HL expansion is also equal to V1 square minus V2 square by 2G, which is known as the Boda-Carnot equation. To set the pipe entrance, for sharp edges the KL is equal to 0.5, then for rounded edge KL less than 0.5, and for redundant entrance KL greater than 0.5, and loss at vent, valve or pipe fitting etc. Then HL is equal to KL into V2 square by 2G. That V is equal to under root 2GH, use only when head loss is negligible, and by increasing the L, VL will decrease, then K will decrease and HF will increase. And also If D increase, the value of Q increase. Then after there is one more notice there. F is equal to function of Re and K by D. Then for turbulent flow, first one is for smooth surface, F decrease with respect to Re increase, and for rough surface, initially F decrease with respect to Re, then F will increase with respect to Re. And third, for the same Re, K by D will increase and F will increase. Then after the fourth one is after critical Reynolds number, K by D will increase and F will increase. Here up to Re critical, F will constant. So this is all about the second chart of fluid mechanics, in which we have covered fluid dynamics, then after laminar flow, then after turbulent flow, and at the end the flow through pipes is there. Now in the third chart of the fluid mechanics, we will include the boundary layer theory, then after the dimensional analysis, and the last one is the hydraulic turbines.